Alright guys, welcome to another one of my great recorded lectures. This time I think I figured out a way better way to do it that's not going to be so sloppy, but we'll see. So I'm going to try to get through these next 19 slides pretty quick, and what I'm going to do is I'm going to try to tell you guys what to write down so you're not stuck writing down every slide, because that's what I don't like about PowerPoint. But you'll see that I uploaded a PowerPoint to kind of organize things better, but I can kind of guide you through what's going to be the most important. So the first thing I want to start off with is this is going to be a lecture on just minerals. Okay? I'll kind of tell you what rocks are throughout the phase, but you kind of learn rocks are actually made of minerals, but it gets a little confusing, and we'll talk about why that is later on. So, what is a mineral? So, don't write all this down. I mean, you can read it. A mineral is a naturally occurring solid crystalline substance, generally inorganic with a specific chemical composition. But chances are you're not going to remember all that by memorizing that sentence, so what's better is let's just write down a couple of key components of a mineral. So a mineral is natural, meaning it's non-man-made. It's solid. One key point I want to talk about here is there's a reason that that minerals are the basis of geology. Geology, when you really think of geology at its biggest unit, is the planet. So why is our planet solid and not a big gas ball like some of the other planets? Well, it's because it's made of mostly minerals. So we'll talk about, so minerals are solid because the chemicals that make them up are also solid in the way they form. So how do they form? They usually form crystalline structures. So I would also write this down as well. And I know I'm talking kind of fast because I want to make sure I try to keep this lecture under 10 minutes if I can. So if you need to pause it to take some of these notes, that's totally fine. So they're not part of the tissue of an organism. You don't really need to write that down, but it is important to know that the key word here is tissue. So some once living organisms can build actual rocks, and because their like shells have minerals in them. But it's not the part of their actual tissue. It's more of their shells. So that's why it's still usually they're inorganic, meaning non-living. And you don't need to worry about any of this. So the main three, they're natural, solid, and they're organized in a crystalline structure. They're generally not made of living tissue, but they can be a part of what animals use for like shells, etc. So you'll actually see some of that. Okay, so one big question that we will be answering later on, not in this lecture, is why do some form really large crystals, and why are most minerals actually pretty small crystals? And it has to do with how the crystals grow. Large crystal growth is rare because it takes a certain set of conditions that doesn't happen in nature often. What happens is usually these much smaller crystals. But this actually leads me to another question that we are going to try to answer in this lecture, which is, what is a crystal? And that might seem kind of like a dumb question because you're like, okay, we're looking at a crystal, but what I want you to do is think of what is the chemical composition that makes up a crystal? Why do crystals look like that? So to understand that, we're going to look at sodium chloride, okay? So sodium chloride is sodium chloride is actually a chemical molecule, okay? And what you actually see in sodium chloride is that it's made up of, sorry, I'm kind of trying to edit here. It's made up of these two elements, right? Sodium and chlorine, okay? And I kind of already circled those for you, but sodium and chlorine. We call it sodium chloride. And this is table salt, right? So this is actually what you see when you eat at the dinner table. But why crystals? So sodium chloride can help us answer this question. So first of all, you've probably never seen a salt crystal quite of sodium chloride or table salt quite as large as what you see here. But it does happen. In fact, people that mine for salt find crystals like this all the time, and they just break them up, and that's what you put on your food, because obviously you don't want to put a giant crystal that large in your food. But anyway, so the big question is why sodium chloride? And so to answer that, we actually have to remember what we know about ions. So sodium is actually positive, and chlorine is actually negative. And what we need to know, if you remember an ion, we talked about why those form in the last Edpuzzle video, so I'm not going to go through that now. But what we do need to know is an ion is anything that's charged. So, and what you also need to remember is that positive attracts negative, and they form bonds. But you also need to remember a key to this is that in order to understand why crystals form, is that positives also do not like to be next to other positives, and that negatives do not like to be next to other negatives. So you have this issue when you're trying to form a mineral. If you remember what a mineral is just these chemical compounds repeated over and over again, right? And in order for us to see them, they're repeated over millions and billions of times because they're so small. But at the really smallest scale, what forms the crystal is how they line themselves up, and it all has to do with those charges I was talking about how some like to be next to each other and some don't. So they have to kind of compromise, and what the result of this compromise is a crystal. What do I mean by compromise? Well, if the sodium ion, as we said before, is positive and the chloride ion is negative, then they need to orient themselves where they're still next to each other, but that you're not going to have too many positives next to each other, and you're not going to have too many negatives next to each other. So what this does is it actually creates this really organized kind of cubic structure where you see that not too many greens are next to blues and vice versa. Not too many blues are next to blues as well. But you still have those blues next to the greens because they like to be next to each other. And so when this happens and it repeats over and over and over again, you get a crystal. And there are a lot of crystals have this same kind of geometry to them, and you're going to notice a lot of minerals do look like that. So that's one way to know the difference between a rock and a mineral is a mineral will usually be very crystalline looking. But there's a little bit more we have to go into, and I remember in the last chapter we briefly talked about ionic compounds, but it's going to be important that we talk a little bit more about them. So an ionic compound, all you need to know, we don't need to write all this down, is that most minerals are this type of compound. That positive negative attraction is pulling them together, right? They're getting pulled together, but they also form those crystalline structures because they don't want too many positives next to each other. So the positives try to stay on the other end. That looks like an X, it's supposed to be a plus. Okay, so most of these most minerals are formed from ionic compounds, which are pretty strong. So these crystallized structures are pretty strong. And we'll keep moving on. So cation substitution. So you don't need to write this down, but you might want to write this down right here. So various cations can substitute for each other in many minerals. They'll have the same crystal structure but different chemical composition. So first of all, what the heck is a cation? So even my chemistry students get this mixed up, but if you just think about it if you just remember the definition, then it's pretty easy. Cations are always going to be the positive in the ionic compound, and there's another word, anion, and that will always be the negative. So anion goes with negative, cation goes with positive. So whenever you hear me refer to a cation, that's the positive, that's usually a metal. And your anion is whatever's going to be negative. So what happens is you'll get these anions, okay, the negative compounds, and they can bond to different cations and have the same crystal structure but different chemical composition. So it's a different mineral, but they'll still crystallize and look similar. And that's what we find with a lot of different minerals. So in the last case we had Na, which was our plus, okay, and Cl minus. Okay, and so when those bond and they form those crystals, right, we have another Cl over here, another Na, and remember it forms that 3D structure, you get what looks like table salt. And you guys have seen that before, table salt crystals. Well, what you've also probably seen before is Epsom salt. And Epsom salt is actually magnesium chloride. And you maybe put this in like baths and stuff like that. And so in this case, magnesium has been substituted out as the cation with chlorine. And so they still form these crystals, but it's a different chemical composition, different mineral. Okay? So you need to understand that over some more specifics. So before we move any further, I need you to know this idea of cation substitution. But before we even look at that, you need to know what a cation is. So what is a cation? Well, it's very simple. A cation is just the positive. It's the positive ion. And the way I remember that is it has a T in it, which looks like a positive sign. Okay, and it'll usually be on the left side of the chemical makeup, and it's usually referred to as a metal. Okay, and this is opposite of what we know as an anion. Okay, an anion is going to be usually on the right side, and it's what we refer to as a nonmetal. So it's anything that's on the periodic table that's a nonmetal. And if you don't know what that is, I'll explain to you probably after the lecture if you have that question. And these are negatively charged. So cation positive, and there's an N right here, which I usually associate with the negative. So what you need to know about cation substitution is that you could have many different, you could have the same anion, okay, and we'll use our NaCl as an example. So you could have Cl minus as your anion, and we could replace that with magnesium, and it's going to have a similar crystal structure, so the crystals are going to look the same, but it's going to have a different chemical composition. And what you'll actually notice, NaCl is table salt, magnesium chloride is actually Epsom salt. And if you ever looked at Epsom salt versus table salt, they're very similar, okay, but they are two different chemical compositions. And you're going to see this throughout the next couple of slides that the anion is going to determine the type of mineral, and then there's going to be a bunch of different minerals in that same class because the cation or the metal is different. So let's take a look at the first one we need to talk about is the silicates. And so I'm going to be moving through this fast, so if you need to pause, don't be afraid to pause to take notes. So silicates are when the anion is this chemical right here, SiO4, 4 minus. That's a silicate, okay? And so remember, that's the anion. Now remember, if I throw any kind of metal here, and you can see down at the bottom here, there's a lot of different types of silicates, because remember we talked about cation substitution. There's a lot of different metals down here that can, and even metals can combine with each other, like potassium and aluminum, and they combine with that SiO. And so silicate can actually be, there's many different forms of silicate. So what I tell students is just remember, if you see SiO on the right side, you're dealing with a silicate, okay? And then the metal, remember, so that's the anion. So silicate is the anion. And the metal is on the left side, and that's, in this case, Kal. Okay, those are actually two different metals, but remember those are going to be on the left side, and those are your positive charges. And remember, the positive, when they combine, counteracts that negative. So when you actually draw the molecule up, you'll see none of these have negatives next to them. Okay, and that's because they're no longer ions when they form that ionic compound. They're no longer actual ions. So silicates, one thing you might want to know is that they are the most abundant minerals in Earth's crust. So most of our minerals have silicates in them. So if you just go in your backyard and dig up some rock that you find, it most likely has silicate minerals in it. And here's a picture of a rare type of silicate, quartz. So quartz is not actually that rare, but when you find quartz with these gigantic crystals, that is rare. But that is a silicate. We already talked about this, so silicates can form with many different types of minerals as their cations. Remember cation substitution, so just know that. There's a lot of different metals out there, and you'll see that throughout the next couple slides. So carbonates form, and these are also some very, very common minerals in Earth's crust, not as common as silicates, but carbonates form when you see CO3 at the end. So it could be any metal here, so X is kind of just my variable I put, right? Any kind of metal, and then you have carbonate. Now remember, carbonate is actually CO3 2 minus, but like I told you before, when it actually bonds with a metal, those negatives go away because they balance each other out. So for example, calcium carbonate, we call that calcite. And you can see there's a lot of different ones down here. Again, you don't have to remember all those, but you can see there's some common ones you've probably heard of, like limestone. And actually, carbonates are what a lot of sea creatures use for their shells. So when they die, their shells can actually form types of rocks that are made out of carbonate. Right here. So you have calcite, two different forms of calcite, kind of naturally occurring calcite, and then calcite that's been used by animals for their shells. You also have smithsonite, so that's when zinc, the metal zinc, gets involved with carbonate. Oxides. Now, oxides are some of the most important for our current way of living, because if you want to get any kind of metal ore, so if you know anything about like where our metal comes from, like iron, which is in all of our buildings and cars and all of that stuff, they come from metal ores. And what metal ores are is basically when you have these oxides, these metals usually don't come to us in just the form that we need them. So you don't just pull, a lot of the time iron, you can't just pull iron out of the ground in the form that we use. What you actually have is iron oxide. So whenever you see an oxygen attached to a metal, that's called an oxide, okay? And remember, I'm kind of repeating myself now, but remember, it's when that iron oxide repeats itself over and over again, millions of times, is when we actually see it as iron oxide. Remember, these compounds are really, really, really small, but I just feel like the need to keep repeating that. But yeah, so the metal ores are extracted. So the iron is extracted, the oxygen is broken off, and that's how we use it. But if we didn't have these oxides, then we might not be able to get the metal. Some common metal oxides, or just oxides that you've probably seen if you've ever driven across the country. Hematite, this is iron oxide. It's actually iron 3 oxide, but you don't need to know why that is. But basically, why is it red? It's because that metal is starting to rust. Okay, so that iron rusts when it's, and that's why we see that pink. Sulfides, same process, same concept as before. So when the anion is a sulfur, and sulfur is a 2-, and it combines with any kind of metal, like right here we see PbS2, the negative goes away, and when that's repeated over millions of times in a crystallized format, you get lead sulfide, which is also known as galena mineral. And when we see it in its pure form, that's what it tends to look like here. So it's a very beautiful type of mineral. There's sulfates. So last one was just an S by itself, but if we have a sulfate, that's SO4 2-. When that combines with a metal of any type, like in this case if it's calcium, you get gypsum. Okay, and there's two forms of gypsum. There's gypsum anhydrite, and then there's gypsum with oxygen. And you don't need to know what that means, just know that basically when there's oxygen attached to the calcium sulfate, okay, and it's very beautiful. Okay, and then there's also a different form of gypsum that has the water molecules removed. But all right, well, that's it for today. I hope you guys kind of understand the different classifications of minerals and how the chemical composition works. And I'm sure there'll be a lot of questions because this might have been kind of confusing. So that's what we'll spend the next part of class doing, is kind of maybe clarifying on some of these. But all right.